going to pick up right where we left off yesterday with a weirdly green screen. That's fun. You see that okay? That's not better. Turner, could you hit the light switch that's labeled screen? If we turn that off, that's a little better maybe. Is that better? You guys see that okay? Okay, enough. All right. So we're gonna pick up where we left off yesterday. We talked about x squared, and don't worry too much for right now about what that function does or specifics, but the shape of the thing was something like this. We found its domain and range, and noticed from looking at some points that it's symmetric with respect to the y-axis, right? So again, like if you folded it over the y-axis, or if you held the y-axis still and flipped the paper upside down, the graph would kind of line up with itself, right? The y-axis acts like a mirror. And then here, we basically proved that that's what's actually going on, right? By finding f of negative x, we plugged that in, we did some algebra, we ended up back with exactly the thing that we started with, right? A thing that is identical to the original function. That's, sort of proving that this y-axis symmetry thing that we've noticed from the graph is actually happening, and that it happens everywhere. Not that, it just happens in this little piece of the graph I'm looking at, but like it's always true for this thing. That's a property that we call being an even function. Again, means that these things are identical and that it has y-axis symmetry. Those ideas are pretty much like tied together, right? Y-axis symmetry means it's even if it's a function, and even function has y-axis symmetry. So the thing I asked you to do was to do the same stuff for x cubed. There it is. There's some points highlighted. So first, just maybe thinking through that this is a function. One way to test graphically is by imagining vertical lines, right? So x values, we want to pair with just one y value. Or in other words, does it pass a vertical line test? Can I draw a vertical line anywhere that would hit it more than once? This is a function then, right? What are its domain and range? Yeah, everything. Why? How do you know? Do it. Okay, the ends keep going. Yeah, what I see kind of here in the middle is this kind of nice smooth curve thing, but nothing's like left out or skipped over or anything. And the ends keep going, right? We got one pointing down to the left, one pointing up and to the right. If we're talking domain, we care about the left-right part. We care about the x values, right? Or if you want, you think about sort of smashing it all down onto the x-axis. Everything we get covered up, right? It's the whole real line gets covered if I do that, because one of these ends is pointing to the left, the other is pointing to the right. So the domain is all the real numbers. For the range, we do the same thing, but turn it sideways, right? Turn the graph sideways, turn our head sideways, whatever, but look at the y values. If I crush it in this way, then the whole y-axis gets covered, right? Because one end is pointing down, the other is pointing up, and nothing's like skipped over or left out in the middle, right? Okay, so the domain and the range are both the whole set of real numbers, or negative infinity to infinity if you want to write it as an interval. Okay. So what about these points I've got labeled? The thing we spotted yesterday with x squared to recognize the y-axis symmetry is that everything's sort of paired up, right? Every point had a point kind of directly across from it that had like the same height but opposite x value. What's happening here? Yeah, I mean they're all kind of matched up again, right? And everything's got a buddy. Look at two of them though: 327, -3, -27. They're similar in that they have the same values, right? and 27, but what's different? The negatives, the signs on not one, but both of the coordinates, right? Okay, so we can often think of a negative sign as being opposite, right? Think about just like a number line, 2 and -2, right? Those are opposites in just like direction. That's what's happening here. 3, 27, -3, -27. Well, just look at one coordinate at a time, 3 and -3. Okay, so they're on opposite sides this way. 27 and -27, they're on opposite sides this way too, right? Same thing happens for the other, sort of pairs, right? They're opposite in both ways. So what's the thing that acts like the middle, the center of what's going on here? 0, the origin, just the point 0, 0, right? Instead of being a whole line that acts like the mirror, it's a single point. So there are 2 ways you can think about that. You need to think about it as like backwards and upside down, right? So it's like flip twice, or put a tack in the graph at 0, 0, so only that point stays put, and spin it upside down. You get a thing that looks exactly like this, right? If I spin it exactly, upside down 180 degrees, then this is going to line up exactly with what's already there. So it's called origin symmetry because the origin, that point at 0, 0, is the thing that works like the middle, right? Origin symmetry, or you can think about that as being like opposite in both coordinates. Origin symmetry is a little bit weirder and a little bit, you have to like kind of train yourself a little bit to spot it a little bit more than y-axis. Like y-axis is a little bit easier of an idea to get your head around because it's like folding a sheet of paper in half. So here's another thing that's origin symmetric, or close to it, depending on how well I manage to draw it. Yeah, that works. That's origin symmetric. Again, with artistic license, but because this is the thing that acts like the middle. The stuff that's in quadrant 1, the quadrants 1, 2, 3, 4, right? Start up here and go counterclockwise. The stuff that's in 1 looks like the stuff that's in 3, but upside down, backwards, right? And 2 and 4 look the same, but again, upside down and backwards, right? If I had a point right here, its x coordinate would be positive or negative? Negative. It's on the left, but its y would be positive. Its, mirror image point would be down here. X would be positive, y would be negative, right? So again, it's opposite in both senses, right? In both coordinates, the signs are opposite. Okay, so that's what origin symmetry, that's a thing that has origin symmetry. So that's kind of how you spot it visually. Okay, so let's check then. Find g of negative x. This function is x cubed. Take a thing and cube it. Cubing means take now 3 copies and multiply them together. What happens? It's going to stay negative, right? Because negatives cancel in pairs. You got 3 of them, so it's going to end up being negative. And there are 1, 2, 3 copies of x, which we normally write as x cubed. Okay, so it's negative x cubed, but like, what does that mean? What that means is what we did here is flip the sign, right? So we took the opposite thing in the input part, right? That means I went from being over here to being over here, or vice versa, right? So what we did with this is reflect across the y-axis, right? Taking the opposite x value means flipping it over this way, right? Going to the opposite side of the x number line. The thing we got as an answer looks a whole lot like the function that we started with, except that it's opposite in sign, but being opposite in sign there means it's the opposite this way,
right? Relative to the y-axis, or the relative to the horizontal, right? The y values are opposite, so it's upside down. So this says I flipped it left or right. This says I flipped it upside down. There's only like one way I can do this without having to break my arm. Flipped it left or right there, ended up flipping it upside down. Well, that's origin symmetry, right? So
these are called odd functions. And the way you recognize it is that changing the sign on the inside gives you the opposite thing on the outside, right? Or you could write that as something like this. The point, though, is that they're opposite in sign. Right, these negative like factors, these negative minus signs, sitting outside of the thing here. Think of that as an opposite. Inside is x values, so it's flipping horizontally this way. Outside is y values, so it's flipping upside down. This is saying if you're odd, then you do both, right? And you have origin symmetry. Okay, so even y-axis symmetry. Get the same thing if you do a reflection. Odd origin symmetry. Get the opposite thing if you do a reflection. Okay. If you have any questions about that part. Okay. There's nothing else for me to really say about like what's going on. What we need to do is just get a feel for it. So what we're going to do for basically the rest of our time today, this example 3, if you flip over to the back of the notes, there are 6 things here. What I want you to do is graph these. So grab, calculator, Desmos, whatever, graph those 6 things and decide from the graph, does this have y-axis symmetry? Does it have origin symmetry? Or neither, right? There's the third option, right? It can be neither. And what does that tell you about whether the function's even or odd? And some of these are going to look, strange and weird and whatever, but don't worry about that. Just look at the picture and look for the kinds of symmetry we've been talking about. 4th example, here's a blank graph. I want you to draw a thing that's symmetric with respect to the x-axis and then think about it. And then 5, some more examples. We're going to check for whether these are even or odd by working out the algebra. So doing it analytically, right? So that's finding f of negative x, simplifying whatever you need to simplify, and then trying to draw a conclusion based on that. Of course, you still have a graph, so you can use that to check or think through things. But there we want to make sure we're practicing the algebra skills too. Okay, so we're going to take about the next 25 minutes, something like that, for you guys to just work. So go ahead and move desks around, get into groups of 4 or 5, something like that. I'm going to wander around and talk to you, and I'll probably chime in from time to time with some stuff. Okay, so let's talk about some of these graphs. So because of the way I got the thing laid out, I'm going to go ACE first, so we'll go down the column. So this first one looks like that. So what do you think? Either? Why? Okay. Yes. So yeah, I mean, some of these it's subtle, and I picked them on purpose because of that. This does pass through the origin. It does have kind of the right shape, right? It's got the same kind of like self-symmetry kind of thing, right? It's the same shape as x squared, but what we're talking about is it symmetric with respect to the y-axis?
So if I hold the y-axis still and flip it over, do I get the same picture? No. Same shape, but wrong place, right? It would move to the other side. If I hold the origin still and spin it upside down, well, for sure not, because it's going the wrong way then, right? Okay, so this is neither. Because again, even though it has kind of the right, shape, and I can kind of, see some of the stuff that we've been talking about, it's not like all there at once, right? It's not in the right spot to do what we're actually talking about. Okay, C is 3x cubed plus 2x, that one. Back in the normal window, there you go. Part C, what do you think? Origin? Okay, how can you tell? Okay, yeah, you could actually work it out, right? Or we can tell from the graph, if you wanted, you could maybe kind of like highlight some points and look at them, right? And see that, okay, they've got the same coordinates, but the signs are opposite, right? It does pass through the origin. If it goes through the origin at all, it's got to be in the middle of the graph, and that looks like, sort of the middle, right? Again, in this weird new sense of middle that we're kind of in the middle of developing. But so yeah, this is origin symmetric, which means it's an odd function. And for our purposes, those things are basically synonymous, like origin, symmetry, odd function. Those are going to go together. Okay, and then part E, the square root. That is y-axis, so it's even. Y-axis goes right down the middle of that graph, and the two sides look like mirror images of each other. All right, everybody agree on all those? Anything we need to talk about with those three? Okay, cool. Let's look at B, x cubed minus x squared. Now again, it's a little bit subtle, right? This might be one that I want to zoom in on a little bit. What do you think? I mean, y-axis is out, right? For sure, it doesn't have that. Origin, though, well, it does pass through the origin. I can kind of see sort of some sameness kind of thing happening from the graph, but it's not in the right spot, right? It's not in the right place. If I held the origin still and flipped it upside down, well, this little bluey thing would end up on the opposite side of where it should, right? So again, it passes through the origin, but the origin is not in like the middle of the graph, right? The middle of the graph would be somewhere over here. So I'd have to sort of move it over and up a little bit to get that. So this would be neither then, right? Because again, it's got kind of the right shape, but it's not sitting in the right place in the plane, right? So we got to sort of think about both of those things. All right, negative 3x squared plus 2. Y-axis. So it's even. Again, y-axis is passing right down the center of the graph. And the last one, 1 over 4x cubed, which is weird, right? And I saw some, alarmed faces when the graph came up, but it's weird. It's in 2 branches instead of just a single piece. We'll worry about the details of that in a month or something, but for now, just take it as what it is. Does this have y-axis symmetry? I'll hold the y-axis still and flip it over, so I get the same thing. No. Does it have origin symmetry? If I stick a pin at the origin and spin it upside down, do I get the same thing? Yeah. This would end up right there, right? You spin it upside down, or if you flip it twice, if I go this way and then upside down, this would line up exactly with that, right? So this is origin symmetric. Okay, cool. All right, so what did you come up with for a graph that's symmetric with respect to the x-axis?
X-axis is right there, right? So the idea here is if I, put something in the top half of the graph like that to get X-axis symmetry, it'd be like if I, flip this line over and whatever ended up there, or if you like drew it on a sheet of paper and folded it over that line and rubbed really hard so the pencil rubbed off, right? So the sort of mirror image of that would look something like that, right? It doesn't have to be this picture, but something where the X-axis acts like the center, just like we've been talking about with the Y-axis, just turning it on its side. Okay, so there's a thing that has X-axis symmetry. But what do you notice about it? It's not a function. Why not? One way to check for whether a thing is a function is to use a vertical line test, because being a function means each X goes with just one Y, right? So a vertical line checks for X values. And what am I looking for when I do a vertical line test? Does that ever hit the graph more than once? If it does, there's an X value that matches up with more than one Y value. It's not a function, right? Well, is it because I just happened to draw this one? Check yours, whatever you came up with as an example of something that's X-axis symmetric. Still fails a vertical line test, right? Because being symmetric relative to that line means everything up here has a buddy down here, right? Well, that's an X value that's got two Y's with it. So can we ever have a function that's symmetric with respect to the X-axis? No, right? Because it would have to, if it has that symmetry, fail a vertical line test. Not sure if I spelled the word vertical right there or not. Or if I just don't know how to make my letters. Okay. It would have to, if it's got that kind of symmetry, it would have to fail a vertical line test, right? Okay. All right. So about 15 minutes left. Checking analytically whether a function is even or odd or neither, which again means finding f of negative x. Now, this would be the first of several places that we'll see this semester where there's more than one way to think through this, right? You just did a bunch of problems where you looked at a graph and checked that way. You can still do that. You have a calculator. I'm not going to take that from you. But on something like a test question, if I asked you to do it analytically, that means you need to actually, do this computation, like work through the algebra, because part of this is, balancing, like building those algebra skills too. But of course, you're still free to like use a calculator to check, and so you kind of know the answer going in, right? Okay. So what we're going to do is actually compute f of negative x, and then use that to figure out what's going on. So let's take a look at maybe C as an example. F of x is x to the fourth minus 5x plus 2. The thing you need to do is find f of negative x. So let's take a couple minutes just now, do that one. Take this function, evaluate it at negative x, talk to your group about setting that up, simplifying, and then once you've got it simplified, what does that mean? Like, how do I actually conclude something from that? Once you work through the algebra, you might, look at the graph and use that to help you decide like what you actually take away from it.
Okay, so what do we think? What's the answer? Is it even or odd or neither? Okay, even, but there was a question mark at the end. I mean, right? There was. You want to do it up at the end. Even, anybody think odd? Neither? Maybe? Okay. So looking at the graph, what do you see? Looks like neither from the graph, okay? Because again, kind of like in the wrong place. Let's see what happens here. If I plug negative x into the thing, that means just anywhere there was an x before, we'll replace it with negative x, right? All right, somebody set that up for me. Negative x to the fourth, right? As a like quantity, as a whole thing to the fourth, minus 5 times negative x plus 2. Okay. Well, now we're in, once we've done that substitution, replace that. Now it's like simplify the algebra time, right? So do the stuff that's written there. How can I simplify this? This means 4 copies of negative x, right? So what happens when you multiply 4 negatives together? Result ends up being positive because they cancel in pairs, right? Okay, so it's going to be positive there. And there are 1, 2, 3, 4 copies of x. So it's x to the 4th. Right? Is everybody okay with that part? Okay, what about minus 5 times negative x? That becomes plus 5x, right? The negatives cancel when you multiply. Plus 2. Right? Everybody agree? Okay, cool. So there's that. Like we've done the algebra, we simplified the thing. But then what? What are we looking for? Whether they're the same, the original thing, the function in blue, or and the one in pink, whether they're the same or opposite. Okay, so looking at those, what does same and opposite mean? Are these exactly the same? No. Almost, but what's different? That right there, right? First one, the original function's got minus 5x as that middle term. The one that we found, the reflection, has plus 5x as the middle term. Okay, so they're not exactly the same, right? If they're not exactly the same, can't be even. Because being even means that its y-axis symmetric, which means that they're exactly the same. All right, well, it can't be even. Is it odd then? There's 3 options, right? Even or odd or neither. So we don't know yet. Odd would mean opposite. Totally, completely opposite in sign. Like multiplying by a negative. Are this and this opposite in sign? No. Some of the terms have the same sign, some of them have different ones, right? Okay, so it's not opposite. Opposite would mean that like anywhere there was a positive, there's a negative now, and vice versa. Or it would mean like I took this and multiplied the whole thing by a negative sign, right? All the way through. Well, that would be minus x to the 4th plus 5x minus 2. That's not what we have. We have a different thing, right? We have a different thing that's sort of like mixed between the two. Well, it's not opposite, so it can't be odd. It means it's got to be neither. Because again, that's the only other option. Which means it has no kind of symmetry that we care about at the moment. Again, it might have some kind of like self-symmetry thing, but we're not interested in that at the moment. Okay, so one more time, there's kind of 2 things here, right? One is just doing the algebra, right? Doing the substitution, plugging the thing in, simplifying. The other part is then, okay, what do I like learn from that? What does that tell me? The checks are, do I get the exact same thing I started with, right? Do all of the negatives like cancel out and just get back to the original function? If so, it's even. If not, well, did all of the negatives turn into this thing being totally opposite in sign? That doesn't happen here, but if it did, it would be odd. This is neither. All right, so we got a little bit of time left. Why don't you guys give maybe A and F, give those a shot. Work through just kind of setting them up, see what it looks like. and see what you think based on that. Operations with microphone, I guess. One more time, remember too, you can, look at the graph of the thing and use that as a way to check what you think is that. Me saying that I want you to do it analytically means you need to like work through that and show me that work, but you can also just, check yourself. Yep. Just like if you're gonna plug two in, rewrite it, that's the two someplace to exit. You do the same thing, just with negative X, that does that reflecting thing.
All right, somebody set A up for me. Function's the absolute value of 5x. We want to, again, do this reflection, so replace the x value with negative x. So what's that look like? Yeah, so it'd be 5 times negative x, or absolute value negative 5x. And then how do we simplify that? Again, absolute value still. Right, so what the absolute value does is measure distance in like a number line sense, and we don't care about direction. So the absolute value of negative 5x is the same thing as the absolute value of 5x. If you look at a graph of this thing, it's like a real narrow, like V-shaped graph, kind of, right? That comes down right at the origin. So is this even or odd or neither? Even, why? Because that and that are exactly the same. So this is an even function, which means it has y-axis symmetry. Everybody agree? Everybody okay with that? All right. Okay, what about part F? So again, the setup, same idea, replace x's with negative x's. Then simplify. How do we simplify that? Okay, so negative x times itself 3 times, or 3 copies, ends up being negative x cubed. And the other one, you got negative x times itself, right? 2 of them. So that ends up being x squared. Okay, so even or odd or neither? You say even or neither? Sorry. Neither? Why? Okay, it's definitely not the same as the original, right? So it can't be even. Being odd means it would have to be opposite in sign. Okay, anybody look at the graph for this one? And what's it look like? Okay, that's fine. I mean, maybe not everything's, maybe it doesn't look like what you expect or something, but does that have origin symmetry? Sure looks like it. What's it mean to be odd again? How's that show up here? It's got to be opposite in terms of the sign, right? Okay. Is this with a negative sign out in front of it? If I cover that negative sign up, is that the same as the original thing? So this is opposite to this in terms of the sign, right? Now that doesn't mean, this is the point I'm trying to make, that doesn't mean everywhere there was a plus, it turns into a minus, and vice versa. It means that it's the same as if you took the function and multiplied it by a -1, right? Just multiplied the whole thing like as a quantity by a negative. That's what it means to be opposite in sign. The reason that what's happening here is happening and why it looks a little bit different than maybe we expected. You don't distribute a negative through a power, through a square root, right? Like you don't distribute inside a root or a group thing like that. That's why it looks a little bit different. But this is opposite to this in sign. So this is an odd function. Right? It's as if I took this thing and just stuck a negative sign out in front of it. That's what it means to be odd. So this is an odd function, which means it has origin symmetry. Okay. There are